Hey, what's up, and welcome back to the series Build a Large Language Model from Scratch. In previous video, we discussed about the byte pair encoding and data sampling with a sliding into approach. Now, in this tutorial, we discuss about the token embedding and the positional encoding, or you can say the positional embedding. Okay, so first discuss about the token embedding. Let's say token embedding. So you know that computer needs some kind of numerical representation. See, numerical representation of word, because computer are unable to process the raw text, or you can say categorical types of data. That's why you need to convert them into some kind of numerical. That's mean to represent the word into some kind of numbers. So you already do it in our previous tutorial, in tutorial number 2 and the tutorial number 3. So if you don't check it, just go and check out in our playlist. So what we actually do, we first convert the sentence. Okay, first we convert the sentence, let's say sentence, into some kind of token. Some kind of token. We also assign here some kind of token ID. Okay, we already discussed that in the byte pair encoding as well as sliding on the approach. And we also discussed about how can you create here one simple tokenizer using Python. If you miss this out, please check. Now, the question is about we already represent them into some kind of token ID. See, that's when let's say I having one word called cat. Let's say cat. So you also give it here some kind of random token ID. Let's say for the cat, I give it here as a 24, and for the dog, let's say I'm going to give it here as a 68, and for the book, let's say book, I give it as a 3, and for the puppy, let's say puppy, I just give it here, let's say 65. Let's say cat, let's say dog, let's say book, and the puppy, I just give it here some kind of token ID. That's my token. That's my token ID. Now I need to put them inside the embedding vector. Okay, I need to put them into the embedding vector. So let's see one images that you already see in the tutorial number 2 as well, from the book Built a Large Language Model from Scratch by Sebastian Rashka. So this is the book that you can see. So you already see this kind of diagram before in our previous tutorial. So you can see it nothing but one GPT like decoder only transformer. You know that why decoder actually used in case of transformer. So GPT is nothing but one kind of decoder only transformer, and the bird is one kind of encoder only transformer. So in here in the example you can see it give it here one kind of input text. This is an example, and it will convert them into some kind of tokens, as well as it will give here some kind of token ID. Now this token ID is directly put it inside this token embedding. Now the question is, in our case, we are not directly putting here this data or the token ID inside the token embedding. Why? The question is why? Because if you see the token that I actually writing down here, the dog and the puppy have the similar meaning. Have the similar meaning. Let's say similar meaning, or you can see or say that it having some kind of semantic relationship. Okay, it having some semantic relationship. So that's why we cannot putting this token ID directly to the token embedding, because some words are related to each other. So it also does not capture the semantic relationship. You can say semantic relationship like the dog and the puppy. So is there any solutions? Is there any solution that, yeah, it have also another solutions. It's called the one hot encoding. That's a one hot encoding. That's a one hot encoding. But in case of one hot encoding, it also having the problem. It's also having the problem. So we already know that what is actually one hot encoding. You can use the pd.get dummies to use in this one, or in case of machine learning. Okay. So in case of one hot encoding, if I take you an example, let's say I have another word called dog, and let's say I have another word called puppy. So in the case of one hot encoding, what actually happening? In the case of dog, it will creating here one kind of matrix, which on having all of the value as zero except the one value. So let's say 0, 0, 0, 0, 0, and one value is one. Let's say 0, 0, 0. I mean, if you have the let's say I have the 10 words, so rest of the 9 word is nothing but the zero, and for the one word it's nothing but the one. Okay. So in case of the puppy, it will making here 0, 0, 0, 1, 0, 0, 0, 0, 0. That's when you can see that dog and the puppy have the semantic relationship, because dog and the puppy are the mostly similar. So what actually happened in this case? In the case of dog, in the case of one hot encoding, it have in the one in the different locations. In the same case of the puppy, in the case of 100 encoded matrix, it also have some kind of different location. See, different location. That's mean it's also unable to capture the semantic relationship. Now, what the solution actually? The solution is nothing but the vector representation. The solution is the vector representation. Let's say vector representation of the word. Okay, let's say of word. So the vector representation, or you can say that vector can only capture the semantic meaning. Vector only capture the semantic meaning of the word. So in case of the semantic similarity word, we can using here this vector representation of the word. Now let's see one examples. So I just take this example from the Google. So you can see it have the cat, kitten, dog, house, man, woman, king, and the queen. So this is nothing but the word. So you can see in case of the vector representation, it having some kind of features is related to each of the word. So living being, you can see cat is also living being, the kitten is also living being, dog is also living being, because those are the animals. Same kind of the house, you can see minus 0.8. You can see minus 0.8. Okay, minus 0.8. It is the negative value. Same thing for the man, you can see it's positive value. For the woman, positive value. The king is also the man, so positive value. The queen is the positive value as well, because this is nothing but a living being. Now you can see it's called feline, so you can see 0.9, 0.8. For the in the case of dog, you can see minus 0.1. Same thing you can see in the case of actually houses, it's 0 point minus 0.4. So if I see the human, so cat is not a human, so that's why value is nothing but 0.1. Kitten, it having the it had the minus 0.1. In the case of dog, it's 0.4. In the case of house, it's minus 0.5. Same thing for the woman, you can see 0.9. The man is 0.8. For the king is 0.7, and for the queen is 0.8. So this is nothing one kind of word embedding. So in case of the vector representation, we can capture here the semantic relationship. Semantic relationship. You can see semantic relationship based on the some features. Based on the some feature. If you see this graph, you can see cat and the kitten have the similar semantic relationship. That's why both of the data is closures. So you can see man and the woman have the similarity as well, but it's also in the similar case of man and the woman, because both of the people are nothing but the humans. And same thing for the king and the queen, it have the similarity semantic relationship, right? So this is how actually it's happening in the case of vector representations. Now how can you actually creating here the token embedding? Because we see that how can you create the embedding, but now how can you creating here the token embedding for the large language model? How can we create the token embedding for the large language model? So I'm just going to taking here one example, the popular one. Let's say a quick brown fox jump over the lazy dogs. Okay, let's say over the lazy dog. So if I convert them into some kind of token as well as we short them, so we may get, let's say a, then we may get the brown. I just remove this a. Just I'm going to start it from the brown. So let's say brown, and then we have the dog. If I convert them tokens, and after that if I short them, so you can see that brown and the dog, and you have the fox, then you have the jump. Okay, then you have the lazy, you have the over, we have the quick, and we have the d. So what you actually do, the brown, for the brown we have the token id of the 0, for the dog you have the token id of the 1, for the fox you have the 2, for the jump you have the 3, and for the d you have the 7. Okay, I just take it from the book. So what you actually do, we need to convert them into some kind of embedding vector right now, because we first tokenize this sentence into some kind of word, as well as we short them alphabetically, and then we assign here some kind of token ID. Now we need to convert them, okay, convert them into some embedding vector, some called the embedding vector. So in case of embedding, it's nothing but one kind of lookup table. So in case of embedding, we have one embedding weight matrix. We have one embedding weight matrix. Let's say it can say that it's called the embedding weight matrix, that you need to create it in terms of the large language models. So we already have our vocabulary, right? We already have our vocab. We already have our token. We already have our token ID, right? We already have our token IDs. Now, in case of the vocabulary, we need to have also one kind of vector dimension. Okay, you need to also have the vector dimensions, right? This is the output dimension in case of the embedding matrix. So in the case of embedding weight matrix, so we have the x-axis and as well as the y-axis. Okay. So what can happen in this case? We have our vocab size. So which one is nothing but the 50257 in the case of GPT-2, and in the uh, in the x-axis, so we have the vector dimensions. We have the vector dimensions. So in the case of GPT-2, it's nothing but 768. So in the y-axis, we have our token ID because we convert them into some kind of a vocabulary. So for each of the vocabulary, you have the token ID. So it started from 0, let's say 1, 2, 3, 4, up to 50257. And in the x-axis, we have in the vector dimension, which one is the output dimensions, and which one is nothing but 768. So you have in 760 of the values. Same thing for here, same thing for here, same thing for here. Okay, same thing for here. So this is called the embedding weight matrix. So now the question is, how can you put those value? So you can put this value randomly in the case of embedding weight matrix. So initially, okay, initially we give the weight value randomly. Okay, randomly. So we know that embedding matrix is also called as the lookup table. So here we can look all the value from here. We will see that later on when we do the coding part. As well as you can see in the x-axis, we have our vector dimensions. I mean the output dimensions. In the y-axis, we have our token ID, or you can see the size of the vocabulary, right? Now we're simply going to implementing this token embedding using the Python programming language. So now we can start writing our code. So in the tutorial number 3, we actually implementing this code for the actually the byte pair encoding and data sampling with the sliding window approach, as well as we also creating here and data loader using the PyTorch library. Now in this one, you're going to see that how can you convert this token ID into some kind of vector representations, or you can say the embedding vector conversation with some hand-on examples. So suppose we have some following 4 tokens. So let's make it input IDs. Let's say torch.tensor, because you need to convert them into the tensor, right? So let's say torch.tensor, and then let's make it 2 comma 3 comma 5 comma 1. Just for simplicity, I take it here. Okay. Now uh, what you can do for the case of for the sake of the simplicity, we're just taking here the bookkeep size as a 6 and the output dimension as the 3. Because if I see that in this explanation that you already discussed, so you can see we have the vector dimensions. In the case of GPT-2 is nothing but 678. Okay, I mean 678, and the bookkeep size is 50257, which is quite big number, right? So in our case, that the laptop that actually using it just using here as CPU, so it's unable to process it, right? So if you have the access of the Google Colab Pro, you can easily access it, or otherwise you can also use the Google Colab. But in my case, I'm just using my local machine. That's why I just for the sake of the simplicity, I take it here bookkeep size as the 6 and the output dimension is nothing but 3. I mean bookkeep size nothing but means how many token ID it have and the vector dimensions. Okay, so what I can do, I'm simply running this out, and after that I'm simply going to taking here a variable called bookkeep size as the 6, and then I'm going to taking here the output dimensions as nothing but the 3. Okay, in the case of GPT-2 it's nothing but 50257, and in the case of output dimension is nothing but a 678. Okay, now what we can do, simply we're going to give here one random sheet so that the value is not changes at a time. So why? Because see, in the case of the matrix or the embedding weight matrix, so you have to initialize the value randomly. Okay, so if I run in this shell again and again, or each and every time, the value should be changed. Okay, so that's why it's better we can give it here some kind of random sheets. So we can use it here torch dot manual sheet. So let's give it here 1 2 3, and after that you're simply going to creating here an embedding layer. So you can using here torch. So let's say torch dot nn neural network, then you can say that embedding, and then we are going to give it to here the bookup size. Let's say bookup size and the output dimensions. Okay, output dimensions. Okay, yep, dims. Okay, so bookkeep size and output dimensions. So this is nothing but my embedding layer. Okay, so you can say that as a variable name as an embedding layer. Let's make it here embedding, so layer. Okay, now from this embedding layer we can simply go into printing the weights, because you can see it's nothing but the embedding weight matrix, so you can easily access this weight matrix from here. So the embedding layer is also called one kind of lookup table. I mean, you can access the below from here. So let's printing this weight first. So let's say embedding layer dot weight. Okay, so you can see here it give here some kind of random weight. Okay, that you can see random weight based on this bookkeep size of 6 and output dimension of 3. Okay, you can also changing it out, the bookkeep size of 50257 and output dimension as a 768. Okay, so let's try to checking this out, is it working or not, or maybe it's crash or my laptop. So I just make it as a 256. Okay, 256. I don't know it's working or not. Yup, it's working, that you can see, but some of the value is not actually showing up, that you can see. Now we can also printing some specific value from here. So I just take it, make it as a 6 and 3, because I need to also show up here that embedding layer is nothing but one lookup tables. So how can I access the value from here? So we can simply go into printing it out. Let's say embedding layer, and then you can simply go into give it to here torch dot tensor. So we are going to accessing here the value for the 3, I mean the index number 3. So you can see this value minus 4015 and 0966 and minus 1.1481 is the exact similar thing for this one, that you can see in the case of the embedding layers. But in the case of Python, it started from 0. That's why 0 1 2 3, and this value is exactly same. That's why it's called one lookup table where you can access the value. Okay, now inside that embedding layer we are going to passing here. So embedding layer, we're going to passing here our input ID that actually initialized. Okay, so you can simply going to give it to your input IDs. Let's say input IDs. Okay, that you can see how the tensor look like. Okay, it will access the value from here 2, then it has the 3, and it has the 5, and it has the 1. It will accessing all the value from here. Okay, so this is how our embedding layer actually work. Now we discuss about the positional encoding. Okay, so let's go on here and let's discuss about the positional encoding. So let's say let's taking this pen. So we discuss about the positional embedding. Let's say embedding. So we're taking here two examples. So let's take one first example. So it's in my the hand note. So take one sentence called, let's say the frog jumped in the river. So you have another sentence. Let's say in the river jumped the frog. Okay. See, both the sentence have the word called the frog. You can see both the sentence have the word called the frog. Same thing for here, the frog and the frog. Okay. But the problem is about positions. The problem is about the position. Position is different, but the meaning of the word is similar. That's mean it have one semantic relationship. But the problem is about the position of the word is different. So what can happen in the case of token embedding? If you directly passing this out, the position of the word is not calculated. It's not calculated. So because you know that when the transformer architecture is introduced, it's just used for actually translation types. Okay. So in the case of translations, the word position is important, right? So same thing in the case of GPT. In the case of GPT, the word position is also important. So if I taking one examples from, I mean, taking one example from images from this book that you can see by the Sebastian Rushka. So you can see the weight metrics are the same thing, the embedding layer that it created. You can see it's nothing but one kind of lookup table. So here you can access the value for the 5 and the 3 also. Now you can see encoding word position, or you can say the position embedding. So these are our word metrics that we created already. So you can see it have the word called fox jump over fox. So it have the two word fox, and the token embedding is the same. Token embedding is the same, but the problem is positions. But how are you creating here an embedding vector? In the case of embedding vector, the value is same. The value is same. You can see value is same. Okay, so it maybe gives some kind of overfitting problem because data is same, the training data is same, token ID is same. So that's why we actually use here something called the positional encoding. So there are two types of positional encoding actually used in the case of GPT. So one is called the absolute position encoding or positional embedding. Another one is called the relative. Okay, so the types of, let's say, types of positional embedding. Okay, let's say embedding. Okay, गर्मी बहुत है इसलिए ये क्या ना हाथ थोड़ा जम गया, जम नहीं एक्चुअली घम गया एक्चुअली, तो थोड़ा वाटर वाटर फील इसलिए जो मैं लिख रहा हूँ ना वो थोड़ा ऐसा हो रहा है. Okay, so there are two types, nothing but called absolute. So let's say absolute, and another one is called the relative. So the word is called absolute just mean it have one fixed positions, or you can say exact location. And in the case of relative, it has some kind of distance, it having some kind of distance, or you can say how far apart. Okay, how far apart. So in the book they actually talk about this, that what is actually absolute position embedding and what is the relative one. So in the case of absolute positions, it for the each position input sequence and unique embedding is added to the token embedding to the convey it exact location. So in the case of absolute position, the location is exact, or you can say fixed. But in the case of relative, it just calculating the distance from the each of the data point or each of the word. Okay, so if you're taking on examples from the book, so that you can see. So we having on token embedding. So you can see token embedding the similar 111 111 111. But the positional embedding is different. Positional embedding is different for the each of the word or for each of the tokens. And when you putting all of this thing by additions, you have to pass it to the input embedding. So for the each token, for the 1111, the input embedding is different. The input embedding is different because we added here an extra embedding called the positional embedding. Okay, now you can see input embedding is different for the same token ID that you can see. But in the case of this one, we are going to passing here the same input token ID as well as same input embedding vector. So in the case of this one, it may be having some kind of overoperating problem because the model is getting the same data again and again. Okay, but in the case of this one, so model is not going to get confused, it will try to predict it correctly. So that's the difference between this absolute and the relative. So in the case of GPT that we are going to building, we're going to using here this absolute positional encoding. Okay, so we know that the both types of actually positional encoding is aimed to the argument the capacity of the large language model to understand the order and relationship between the tokens and ensuring more accurate and context our predictions. I just it's writing in the book. So the choice between them often depend on some kind of specific applications and the nature of the data being processed. You can either use the absolute or either you can also use the relative. But in the case of OpenAI, they actually use here the absolute position embedding that are optimized during the training process rather than the being fixed or predefined like positional encoding in the original transformer. See, in the case of original transformer, it have one fixed types of positional encoding. Okay, fixed types of position encoding. But in the case of the GPT-2, in the case of OpenAI, they're actually using one kind of positional embedding, which one is also change is parameter value. Change is parameter when you do the training. Okay, so it having some kind of difference between this original transformer to this GPT model, GPT decoder transformer, right? Now we're simply going to implementing this one using Python. Okay, so what I can do is simply going to go on here on the code. So let's taking some more shell, and then after that, what I can do, we're simply going to take the bookcap size. Let's say bookcap size. Let's say bookcap size. Let's take in the original one. Let's say 50257. Otherwise, you are getting quite angry. अरे भाई ये तो नहीं कर रहे एक्चुअल के अंदर एक्चुअल के जैसा नहीं कर रहे इसलिए then we are going to taking here our output dimensions as let's say 256. Okay, now we're going to creating here an embedding vector. So let's say torch, okay, torch dot nn dot embedding, and then we passing here this bookcap size that we created as well as the output dimension. Let's say output or dimensions. That's it. So let's assign into a variable called token embedding layer. Okay, let's say embedding layer. Okay. So previously we creating here a data loader that you can see. We creating this out, create a data loader functions as well as one GPT dataset P1 class for creating the datasets. So now we're simply going to using here this data loader so that you can also load the data in the from a batch, because you know that in the case of neural network you need to load in the data in the from a batch. So you can easily use the data loader that you already created. So what I can do, I'm just going to give it the max length, I mean my context length as the 4, just for sake of the simplicity, just take it here. But later on, how you're implementing or doing the attrition mechanisms as well as the coding the GPT from scratch, we're going to using here the actual token ID, but we are going to do the code in case of the Google collapse. Now we are going to using here this create uh, data loader method that actually created. Now you're going to passing here raw text, I mean our verdict short history, that you can see this verdict short history that you already inputted, and then you're going to give it to here the base size. So let's say base size, let's make it as a 8 at the base size, and a max length, I mean my context length is also my max length. Okay, that you actually give it here in the case of variables. Now I need to also give it here strike. So right now we're going to give it here strike at the 4. So let's say I'm going to give it to the max length. Okay, because you know that if you don't know what is the stride actually, because we already discussed about that, if you see that you can see stride, you have the record start of 4. Just we're taking this example. A start of 4 moves in the input field by the 4 positions, and this is a start by 1. You're already implementing this out. Now in this case, for this position embedding, we're simply going to give it a start as a 4. Okay, and then we make it shuffle. We don't need to shuffling our data sets. So let's make it shuffle as a false. So this is nothing but our data loader. Okay, this is our data loader. Let's create here a variable. Let's say data loader, and after that what I can do is simply going to iterate. You're going to using here an iterator so that it will load here a batch of data in case of raw, in the case of row. Okay, so let's say data, and you also make it the variable like that, data iter, and you're going to using here this iter, and you're going to passing here the data loader so that it can load here in the case of batch size. Okay, now we need to have our input. Okay, we need to calling here our next, so that it will calling here the first base, second base, third base, like that. So you're going to using here this data iter. Okay, so each of the tutorial is connected to the before of previous one, so you need to checking this out. Now you need to give it here the inputs and the targets. It's give me two values, inputs and targets. If you see this one that you already created, that you can see the inputs and target as well. Okay, first base and the second base, and how can you use here the next functions, right? Now it's simply going to copy this out, but you're not going to printing here the input and the targets. You're going to printing here the token ID and the token ID and the token input shape. Okay, let's say it's a token IDs, and then you can say that this is nothing but our input shape. Let's say input shape. Okay, that's it. So in the case of targets, you can simply go into using here input. Okay, let's say input dot shape. Okay, let's see. So you can see the shape of the input is nothing but 8 cross 4, 8 cross 4 tensors. So 8 is nothing but the batch size that you define on here, batch size, and 4 is nothing but my context length. I mean the max length is the 4. And you can see it has a stride of 4. That's why you can see 14, 367, 285, and after this 4, 1464, it will be starting here and new one, because we our max length is starting with the 4. So if I give it to here stride as a 1, then you can see after 1, after 1 it will actually creating the sliding. Okay, that you can see 40367, and it started from 367. That okay. Okay, so after 367 it will creating here the next matrices. Okay, so now we're going to keep it here the same thing that we have in our books. So you can see now input shape is 8 cross 4. Okay, meaning the database and with some 4 tokens. Now let's see how can we use the embedding layer to embed in the each of the token ID with the 256 dimensions. So what I can do is simply going to using here the token embedding layer that we actually created. So let's say token embedding layer, and you're going to passing here the inputs, right? Same thing that we do earlier, and then we have our token embedding. Let's say token embedding. Okay, now we can printing this token embedding, right? Shape. So let's say print token embeddings. Oh, dot shape. Okay, anything wrong? Okay, I just give it to t the double time. Okay, now you can see shape is look like that. 8 cross 4 cross 256. That's mean 8 is pair size, 4 is the context length, and 256 is nothing but our embedding dimensions. Okay, or you can say dimensional vector, 256 dimensional vector. Now, now we need to also add here the positional encoding. So if you see in the book that you can see, in the box you can see we need to joining them the positional embedding, okay, with the token embeddings. So positional embedding is nothing but one kind of embedding as well. The same embedding layer you can also use that, okay, and you can using the absolute one. So that's why the embedding layer is the same as the token embedding that you created. So what I can do, we're going to give it here a variable called context length. Let's say context length, and let's make it as a max length. And then you're going to creating here an embedding, same thing that you created for the token embedding. Let's say embedding, and you're going to passing here the context length, and the output dimensions. Okay, let's say output dimensions. So you are not going to passing here the vocabulary size. You're not passing here the vocabulary size. We passing here the context length in the case of positional embedding, because for the case of position of the tokens, we're going to give it, we are going to creating here an embedding for the each other positions that you can see. For the each position, you're going to creating here and single embedding for this position, for this, for this. Okay, that's why you give it to the context length, because in the context length we having our we have our size of the content. Now this is my position embedding. Okay, position embedding layer. Aha, let's make it layer. And then after that, what I can do is simply going to using here this position embedding layer, and you're going to using here torch dot arrays. Let's start with the context length. Okay, now what is this torch dot arrays actually do? It is creating here a series of the value. Okay, let's say if I give it here 10, so it will start from 0 to 10. Okay, it's nothing but one kind of while loop. Okay, it will start from the 0. So same thing on here, because we have the context length, so it will start from 0 as well, 0 1 2 3 4. So you have the context length of the 50257 that you can see. In this case, how is it? In this case, you can see it can start from 0 and it will go until 50257. But in our case, it's nothing but the 257. Okay, 25 seconds at the max length. So we just give it here the context length. Okay. Now we're simply going to give here the variable. Let's call position embedding. Okay. That's it. Let's make embeddings. And then we're simply going to printing the shape of that. Let's try to printing the position embedding. Okay, position embedding by position embedding dot shape. So this how shape look like 4 comma 256. You don't have any batch because you're not using the data loader. So you're going to using the data loader in the case of token embedding, not in the positions embedding. So that's why we don't use here in the batch. Okay. Now what I can do is simply going to joining here this token embedding as well as the position embedding that we see in the book. You can see in this book. Where is it? see in this book that you can see join them. Okay, now what I can do, you can using here this token embedding. Let's say token embeddings, and then you get using here this position embedding. So this is totally nothing but my input embedding. So let's say input embeddings. Okay, now I can printing the shape of this input embedding. Let's try to printing here the input embedding dot shape. So the shapes look like that, 8 comma 4 comma 256. Okay, so the input embedding is created. Now in the next one you're going to see the most important topic is about the attention mechanisms. Okay, this is the heart of the GPT. Okay, so that's it for today. I hope you enjoy this full tutorial, and make sure to subscribe our channels and share with your friends, and thank you. Bye bye. Namaste.